In this video, we're going to round out our last possibilities, so looking at our Sn equals 6. So this is, again, similar to Sn equals 5, which I didn't say in that video, but these are all expanded octet structures. But if we have 6 bonds around a central atom, what shape does this take? This takes octahedral structure. So we already looked at this previously. But now we're going to start adding lone pairs and seeing how that affects things, right? Now, unlike the trigonal bipyramidal structure that we were just looking at, here all of the positions around the central atom are equivalent. So we can add a lone pair wherever we want. It's all going to give the same structure. So for simplicity's sake, so if we have one lone pair, and I'm going to pick the one on the bottom to do this with, just because then it makes it easier to talk about the structure. So if the lone pair is down here, and we could pick any of these, and it's all the same, it'd just be a matter of which way it's rotated. But we'll still keep our x's along this central plane here, and then one x pointed up. So what we have now here is a square right here, and pointed up to a pyramid, in a pyramid shape. And so the name of this molecular geometry, again, the electron pair geometry is still octahedral for all of these, but this is what we call square pyramidal, because we have a square pyramid. All right, so pretty straightforward. Okay, now then the second question is, so we're going to add another lone pair to the structure. So this is our one lone pair. So again, if we have a steric number of 6 and one lone pair, we get a square pyramidal structure. What are our angles here? Well, they're going to be similar to the angles that we saw previously, but we're going to get this a little bit less than 90-degree angle right here, right? So all this is going to be pushed up a little bit. So it's not going to quite be flat, but rather pushed up a little bit, because this lone pair, the lone pairs just like to take up extra space. They're like they just like to stretch out. Okay, so that's our one lone pair structure. Now, what about two lone pairs? Well, we've already added one lone pair to the bottom, and then the question is, where are we going to add the other lone pair? Now, we could add it along any of the positions along the middle, but that'll put it right next to the other lone pair. The lone pairs want to spread out as much as possible, so the best structure is to put the other lone pair on the opposite side. So then we're still going to keep our x's in the middle here. And now we just have the square. If we ignore the lone pairs now, to think of the molecular geometry, we just have the square now. So this is called square planar, because now it's all completely flat. There's no pyramid to it anymore. So this is the two lone pair molecular geometry we get, is a square planar structure. So again, the lone pairs go on opposite sides because they're just trying to get as far away from each other as they can. All right. Now, in theory, we could go to 3 lone pairs and 4 lone pairs, but these are really, really uncommon, and we won't see these. So we're going to ignore these. These structures can, in theory, exist, but they're very, very uncommon, because once you have this many electrons around, the only way to sort of make it work is to actually have bonds with other stuff around it. So this concludes all of our structures. So let me just pull up. There's some excellent summaries of this. So there's a nice chart in your book. I'm going to see if I can find it to put it here. It might be here at the end. I think this is it right here. Yeah, this is it, except for now it's tiny. Let me just blow that up. But this summarizes everything that we've covered in the last whole set of videos. So this is table 9.1 in your textbook. I'd encourage you to use this. But this summarizes everything that we've talked about. So it has all the different steric numbers, 3, 4, 5, and 6. So it doesn't include 2, because 2 is pretty straightforward. That's just linear. And then it has the electron pair geometry, which is, again, for all the steric numbers that are equal, these are the same. So trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. And then grouping them by number of lone pairs. So we looked at all these structures over the last several videos. 0 lone pairs, again, the electron pair and molecular geometry match. So trigonal planar. But these are going to be different if you have any lone pairs. So again, we have our bent structure. If we have one lone pair, If we go to the tetrahedral, we get our trigonal pyramidal and bent structures. For 5, we get our seesaw, T-shaped and linear molecules. And then for 6, we have our square pyramidal and square planar structures that we just saw in this video. So this is a good summary of everything that we've covered up to this point. There's a lot of information here, but hopefully it all makes sense now that you've seen it, and also has the bond angles, again, including the ones where the lone pairs are pushing on things and causing them to be a little bit less than what you would get in the ideal structure. All right, and so that concludes our first section on molecular geometry, where we've looked at the Vesper theory, right? So this is a good summary of all of this. Is essentially, this is all the valence shell electron pair repulsion theory. This is all of it in a nutshell. And so we're going to get some practice going from Lewis structures to figure out which of these theories are the ones that apply, or which of these structures are the ones that apply to particular molecules. So in the next video, we're going to do a quick practice with a couple of molecules, figuring out how to apply these to specific situations.